Begin physics today, and we're going to be doing the inquiry on springs. You can find that on the website if you want to bring that up. There's eight directions to what we're going to do, and here is an applet that we're going to use. So you can click on this and open up in a new screen, and you'll be able to help me as we go along with this. Okay, so back up there. Here it is, all open. And we're going to click on the intro tab first, and we're going to have this spring, and we can put different masses on it, and it can bounce up and down and stuff, and can't ever catch it once it's off. Okay. So I'm going to open up a Google Sheet. Everybody can see that? I have it blown up enough for you. Okay, and we're going to look at part 1. Part 1 says, in the intro section of the program, which we just went into, use spring 1 and the known masses to record some data and then graph the data in Google Sheets so that the slope of the best fit line will give you the spring constant K in newtons per meter. So how do we do that? We've done this several times. I've told you it's how we discover science. We've practiced it over and over again. How do we do this? How are we going to figure out the K value of this spring right here? What?
Force over displacement.
Okay, force over D is your K value, right? So I have a whole bunch of weights down here. I could put them on here and figure out how far it stretches it. But I'm not going to do that just with one weight. We're going to do it with all these weights. And I'm going to let Google figure out what the K value is. So who wants to explain it a little bit more? We're going to make a graph. Right. So we're going to try to do. We're going to try to make the slope equal K. So what am I graphing? Okay, on which axis?
Your displacement would be the x.
Okay, so if you look at our equation. Whoa. So K equals force over D, right? That's what Dylan said, right? Okay. So I don't want to put one mass on the spring, see what its force is, and then divide it by how far it stretches it. I want to be more precise. I want to do better science. I want to be more accurate with that. So I have a whole bunch of weights. So I'm going to put a weight on there, right? And it's going to stretch at a certain D, right? Then I'll put a different weight on there and it'll stretch at a different D. Put a different weight on there, it'll stretch a different D. And now I have 3 data points, right? I have 3 forces and I have the 3 displacements that they stretched it. So I can graph that data, right? I can graph force and D, and I graph force on which axis? Y, and I put D on the x-axis because I want this, it's going to be a straight line, right? F equals KD, that is a Y equals MX, right? Right? Everybody agree with that? I thought I had a good marker. I have one. Okay. So, or if I just look at this form, that K I want to be the slope, and slope is rise over run, right? So Y over X, either way you look at it. I'm going to graph all the forces on the y-axis and the displacements on the x-axis, and the slope of that should give me my K value. Everybody good with that? Part 1, that's what we're going to do. Okay. All right. So I'm going to go to my spreadsheet here real quick, and I'm going to do this. Huh? You all need to make a spreadsheet, yes. Part of physics is actually learning how to use Google Sheets. It used to be a huge part of it, but this year's been a disaster. So I have some masses. I'm gonna type in some masses here. And what do I have? I have a 50, a 100, and a 250. So I'm gonna do 50, 100, and 250. Okay, I'm just gonna go ahead and put those in there right away because I want to show you some things or remind you of some things. So this column here is gonna be, I need to have my X column come before my Y column, right? So Google knows kind of what I'm trying to do, at least sometimes Google doesn't. So X is gonna be displacement, right? Okay. And Y is going to be the force. Okay. All right. How do I calculate the forces? Mass times gravity, but the mass has to be in what units? Kilograms, right? So I'm just gonna quickly calculate the forces here. How do we do an equation? We do an equal sign. Very good. And then I'm going to get the mass. So I'm going to click on this first mass over here. And what do I have to do to that mass? Divide by 1,000. That'll put in kilograms, right? Then I can take it times 9.81. Right? And this is something new.
Yeah, I got that.
Suggested autofill. Yes, I do want to do that. Now the problem is that we've noticed that doesn't just come up every single time. I don't know why. It's kind of nice.
I assume it's like.
It said like command enter, but and the other things it didn't ever actually give me that option ever again. So maybe it's because I already had these things over here. I don't know. It's weird. Okay, so there's my forces, right? Everybody still with? No? Someone's not? Okay. You all have to print this out here when we're done, so stay with me. All right, so I'm going to go find all these displacements. So I'm going to go to this inquiry. I need a ruler. You can grab the ruler over on the right, and I'm gonna put the ruler just right there on the edge of that little thing right there. Okay. Now we actually have to measure stuff. Okay, so here's where I screwed this up because I could not get my mind around these things looking like they're millimeters. But this whole thing is blown up, and it says down here that these are centimeters. So that's actually 10 centimeters. Okay. So each one of those little tiny things is 1 centimeter. Okay. So if we have that straight, you'll keep me going here then. Okay. So we're going to take the 50 gram mass. I'm going to put it on here. And so when you bring it up here, see it grabs, the spring grabs onto it. So it's kind of hard to tell where we're going to be. So I'll just go ahead and put it on and let it drop. All I have to do is I click the stop button and it'll actually go to the resting point, how far it stretched it out. Okay. And it looks like 5, 6, 7, 19. How'd you get 19? Oh, are you doing it from the bottom of the mass? Remember, I remember this. I put, well, we can't do that because we have to, I put the ruler right where the thing was at rest, right? It was that little point. So it's this little point right there. So I'd say, yeah, 8. Does that make sense? Mine's at 8. I'm going with 8 centimeters.
Wait. Oh.
It's so much easier to look on this thing. I need to start doing that. So I can hardly even see it on my computer. All right, so I'm gonna right here. I'm gonna put in. Okay, what this needs to be in meters. So what is that? 0.08. Okay. All right. Take the 50 off. Put 100 on, and hit the stop button. And 11. Looks like it's at the 11.
It's like at like
Oh, yeah. That's all right. 16. Yeah. I got down there. So you got to keep me. I wasted an entire period the other day because I couldn't read the ruler. It was rather embarrassing. No, it's 0.16. Right? Here we go. Because there was I was saying that was the 10. There's the 10. There's the 15. So one pass there.
This what screwed you up on the last one?
No, what screwed me up was I was counting these as millimeters and I was having that be like 1 centimeter. And then later I switched gears. I just switched in the middle of it and I started doing it the other way. And then I was like, what is going on here? I don't know. It was just, I was having a COVID brain day. Okay, so there's the 250 and there's 40 and it looks like 41 is the end of the point right there. 41 centimeters. So that'd be 0.41. Okay, do we need to wait for anybody? You're all good? Might not seem like it, but we are like already 20 minutes probably ahead of first hour class. Okay, so we're gonna highlight those two. Actually, let's highlight the column, the headings too. Highlight all those, okay? And we'll roll the dice and see if Google can figure out what we're trying to do or not. Sometimes it does, sometimes it doesn't. Insert a chart and whoa. Actually, mine even shows scatter chart. Did any of yours?
Yeah.
It did?
Yeah.
Okay. I have not figured out the logical reason on that. Yesterday, I got a bar chart, first time I did it. Then I changed it to scatter chart and then it was all still screwed up. And then I had to click some stuff down here. So I don't know. No, this is great. Mine's perfect the way it was. Was everybody else's? So everybody has something kind of like this. Okay, so we don't have to change anything on here, which that just put us like 20 more minutes ahead. All right, so customize. Click the customize tab and chart and axis titles. Let's at least put in a chart title. Determining K. That's what I'm doing. Okay. All right, we want to go to the most important part on this customize tab, which is the series, right? Series. And come all the way down and you'll see trend line. That is a really nice trend line. Show R squared if you want to. Ooh, 1. Wow. Okay, I'm going to unclick that and take that back off because I don't really need it. I want the equation, don't I? Who remembers where to find that? Yeah, under the label, hidden in the label is use equation. What's our K value? Yeah, it looks like it's around 6 newtons per meter. Right? Because there's our slope. Y equals mx. So there's our slope. That's our K value. Everybody get it? About 6? Anybody need any help? Don't get so far behind that we're real trouble. Stop me now if you need some help. How do you what?
Jake, how did you manage to mess this one up?
Good job, Jake.
Good job. You followed me.
So proud of you.
Sorry. That was a quick one. Good job, everyone.
No, you just did it.
Change the title.
Yeah, R squared for 1.
All right, we're done with part 1. Only 7 more parts to go.
What? Oh my God.
There's 8 parts to this. What? I told you. This took the entire period in first
But
period.
you said we were like 30 minutes ahead.
I know.
All right, let's keep going.
All right.
Just let them in.
That's part one. Okay, so what I'm going to do is I'm going to come down here. I'm going to be a little fancy. Right here at part one, I'm going to do K equals. Okay. Now, text that actually left justifies. So I'm going to click in that, and I'm going to come up here to the alignment tool, and I'm going to say, put that on the right side of that cell. K equals, and then in here, I'm going to put 5.93. I'm going to hard code it in there. And right justifies numbers. So I'm going to come back up here, and I'm going to move it over to the left. So now I got a cool thing that says K equals 5.9.
Why can't you just put it in one box?
Because we want the
Because I'm going to reference that K value later. Okay. I'm going to reference it. I don't want to type it in every single time. Okay. In case I screw something up and then I want to go back, like first period, I screw something up. It was very easy to fix our problem once we realized because we had done it this way, right? If you hard code everything in, then you've screwed something up, you go back, you got to change it everywhere you put that number, right? That's coding. Yes, it is. It's coding. We're making functions. Okay. No, that won't work in here. All right. Part two. Use spring 1 and its calculated K value to determine the 3 unknown masses in grams. Ooh, this got exciting. Look at, there's 3 unknown masses. They have question marks on them. We might be able to guess. This one looks like a little bit bigger than the 50, but smaller than the 100. Something in there maybe. Okay. All right. So go to your spreadsheet and let's see. What did we have? We had, was it purple? Orange? Blue? Is that what they were?
Yeah.
Purple. Oh, I should have did blue and then the orange. Purple, blue, orange.
Oh, wait, why are you?
Okay, masses. Whoa, it's got a crazy with the S's. Masses in grams, and here's where we're gonna get them all. Okay. So how do I calculate the mass? Okay, so we know force is K times D, right? And what is force? Force is the mass times gravity equals K times D, right? Okay, so I could do mass equals K times D divided by the gravity. That mass will be in what? That'll be in kilograms, and we want it to be in grams. I want to go all the way to grams. So what if I'm in kilograms and I want to go, this will be in kilograms, I want to go to grams. What do I do? What? Times by 1,000, right? So I'm going to times that by 1,000. So there is an equation, right? There's an equation that I can put in to the Google Sheet right now. Okay, right in here. Well, let's do it here. Let's do this. Displacement, right? In meters. We're going to get a displacement right there. And I can do an equation right here. So equals, right? Now, what do we need? We need the, did you all write it down? You can't see it anymore. I need a K value, right? Okay. So you could type 5.93, but that would be a mistake, right? We want to do what? We want to grab it. Okay. Now, if you remember, I think I'm pretty sure I've taught you this before. Eventually, we're going to get a whole equation here, and then we're going to drag it down, right? And we have displacement in here, and that's going to be great because it's going to, the dragging down is magical. It's going to grab every new displacement, right? But the problem is when I drag this down, what's it going to do for the K value? It would try to grab each new K value. We don't want it to. We want it to be stuck, static on that. We want it to grab that every time. So I don't want it to increment its row number. I don't want it, I want it to be C10 all the time. I don't want it to be C11 and then C12. So what do you put in front of that number? A dollar sign. Dollar sign says take that exact place. Now, do I need to put a dollar sign in front of the letter? Technically, I don't, because unless somewhere along the line I drag down and if I drag over, now it's going to be D and E, right? So as a general rule, I know in this equation, I want that exact, I want C10 every single time, no matter what, if I drag down, drag over, whatever. So it's probably safe, even though I wouldn't technically need it this time, it's safe to put a dollar sign in front of the letter also. Okay. So this is always column and row. I'm going to put a dollar sign from the column. I'm going to put a dollar sign from the row because I want to make sure I'm always grabbing that cell. So that was a long thing for how I got the K value. All right, now what am I taking it times this displacement, right? Everybody with me still? Times the displacement, right? Times 1,000, right? Divide by gravity, right? Should we make a constant for that, or should we hard code that one in? We are gonna do different gravities in the next problem. Let's just do it. We'll just hard code it in because I know you guys want to be done and you hate physics and hate learning. So we're gonna divide by 9.81. Okay. And I'm gonna hit return. Why is the mass 0? The displacement was 0. Okay, so I'm gonna drag that down. And then we can run the experiment. So I'm going to get the purple mass. I'm going to put it on there. Click the stop button. Purple mass went down to looks like 12 centimeters. 0.12 meters. So moment of truth, 0.12, and the mass is 73 grams. That was kind of close to what we thought, wasn't it? I'm gonna reduce the digits. Okay, the blue one. You can go ahead and try to figure them all out if you want. The blue one is at 20. Ooh, mine looks like it's at 24.5. That's what I'm doing. 0.245. Ooh, the blue one looks like it's probably 150 mass. That's what I guess. What's this one going to be? This one's going to be a 200, I bet. What?
It should be about 200.
31 to 32.5. 32.5 centimeters, 0.325 meters, and oh. 133. Oh, yeah, 0.33 doesn't make it come out a lot better. What was this one? Is this 0.25? Ooh, that comes out, but yeah, I'll do that. Okay. Good, nice. Part 2, we got that done. Everybody good? So you click on these. You can highlight them all. And then see up here, this is like decreased decimal places and increased decimal places. All right. Can we keep going or not?
That's great.
Okay, part 3. use spring 1 again. It's calculated K value again. And the 100-gram mass only, okay, to determine the gravity on Jupiter, the moon, and planet X. Dun, dun, dun. Interesting. Okay. Celestial bodies. Let's see. What was it? Pluto, or no, it was Jupiter, the moon. Anybody in here know the name of our moon?
The moon.
No one in the other class knew the name of our moon. If you're on Jupiter, you have like a whole bunch of moons: Ganymede, Europa, Callisto, Io. Fancy names, right? Okay. What?
Is it Luna?
Luna. Nice job.
That's just moon in Spanish.
That's its name. Remember Luna Lovegood from Harry Potter? Yeah. Remember their moons with all their symbols. Okay. Planet X. Oh, what did you say? Oh, you did? Oh, okay. Good job. I give you full credit. Gravity. Okay, we want gravity. All right. Let's write an equation for this. Whoop.
Marker.
Where's my
Just press the button. You don't need the arrow. Just press the button.
yeah, but why did that? How did I turn that off? I don't know.
Override does it automatically.
Cause Zoom.
Zoom.
Because of Zoom. Okay, we want to find the gravity this time. So we have F equals KD, right? And F is M times G equals KD. I am.
Okay. So yeah, you're recording on Zoom, so they aren't going to be seeing the screen like the.
Yeah, I'm recording my entire desktop.
Oh,
That's what it's supposed to be. I've shared the entire desktop, and so I don't know if it doesn't work. I got one more period to try it. Then everybody's out of luck. Okay, so then gravity equals K times D, right? Divided by the M. Correct? Okay, that's what we want. So here we go, equals, I need that K value again. See, good thing we wrote it down, huh? Grab it. Okay, and I need to put on dollar signs for it again, right? Otherwise that'll be a mistake and it's gonna mess everything up. Times the displacement, which will be down here. I didn't make my column header yet, but there we go. Okay. Divided by the mass. What's the mass we're going to use? 100 grams. So that'd be how many kilograms? 0.1. So let's just divide by 0.1. Displacement in meters. Sorry, I'm uncapitalizing. That seemed to bother some people.
Yeah, you capitalize Jupiter, Lunar, Planet X too.
What?
You gotta keep it consistent.
I capitalized those. Those are like celestial bodies.
But these are headings.
Oh, they're headings? Okay. Capitalize your headings then.
Don't
Okay.
capitalize all of it. So it's like.
When you turn it in, I'm going to count them wrong if they're not capitalized.
Yours aren't capitalized.
I know, but I'm not grading mine. Okay. Good. All right. I think we're good. Let's do it. Okay. So we're going to get the 100 gram mass on there. Okay. And that's stretched it a little ways, but that's on Earth. So how do we go to these planets? So over here, look at. Let's go to Jupiter. So I click on Jupiter. Whoa. Takes off again. Stop it. Okay. Jupiter looks like it's at 41.5. Go ahead, put 42 in. 0.415. And the gravity is like 25. Because that's what I thought I measured. If you thought it was 42, then put 0.420. Sig figs. What's the G-force on Jupiter? Approximately 2.5, right? G-force is how many Earth gravities is it, right? How many times gravity is it? Gravity on Earth is 10. This is like 25, right? 2.5 times the gravity on Jupiter. Jupiter's a ginormous planet. If you went to Jupiter, you would weigh 2.5 times whatever you weigh right now. I want to ask you. Okay, yes. What'd you say? 0.1? Because it'd be 100 grams, 0.1 kilograms. Okay, good. Whatever, it's fine. Moon. Wow, didn't pull it very far. 1, 2, 2.5. 0.025 meters. What capital? United States Capitol's on lockdown. Uh-oh. Uh-oh. Okay, let's see. Can we make that better? What's the 0.303? 0.027. There, that's what I measured it at. 2.7 centimeters. So the gravity on the moon is like 1.6. Because I wanted the gravity to come out to be like 1.6, because that's kind of what it is. Actually, it's a little bit more. 1.67 is usually what it is. 1. Ooh, yeah, there we go. Okay.
About 7.5.
Just that's what the gravity is on the moon. So I was just trying to make it work out. So I put 0.025 in and I 0.03. All right. Yeah, basically I'm fudging data, which you're not supposed to do. Whoops, I still need that. Let's see. Planet X. Whoa. And 21, 22, 23, 24.
23.5.
I'm going 24. 0.24. Planet X is gravity's 14 on there. Planet X bigger or smaller than the Earth? It's bigger. Has more gravity, right? Don't know what it is, but it's definitely bigger than Earth. All right. Are we all good? Part 3. That was part 3, wasn't it?
Yeah.
Now it's time to go to part 4. Okay, actually, part 4 through 8, they're all one big problem. So, oh, that make you happier? Still longer. No, I'm still going to divide them all up. But it's all one big, huge, ginormous, very difficult to understand. Okay, so on part 4, we're going to go to the lab section. So if you come down here and click on the 4th thing over there, the lab section. Okay. Let's see, what's the first thing it says? It says, now click the lab section of the program. Use the given spring and slide the friction, it's called damping, down to none. So we don't want any friction on here. So over on the right, make sure the damping is all the way to none. Okay. There's a little slider here, see? Make sure it goes all the way to none. What? We're in lab. Yeah. Change it to lab. Okay, it also says make a 250 gram mass on the uncompressed spring and drop it. Okay, so we're gonna make this a 250. We only have one mass on here, or one known mass, and you can change it. So drag it up to like make it bigger and bigger. Make it bigger. 250. Okay. Okay, I'm gonna add some things to this inquiry to make it a little bit better. No, I mean just some in my directions. If you click like the natural length button, that actually puts a nice little line, starting line right there on the point. That'll be good. Okay. Click on movable line so we can have a little laser line we can put anywhere we want. We're going to try to put this at the very bottom of where the mass will fall. Okay. Because we want to get, we're going to remember the other day I was talking about if I came up here, you had a certain amount of energy and we drop it, we're going to figure out the conservation of all these energies. So I want to know where it's starting. I want to know how far it gets down. I need to know that distance. So I'm going to take the 250 on here and I'm going to move it back up. See, there's like an arrow. It's really nice. So I'm going to move it back up so that arrow's flat. So I know that the point's right on the line. You see that? Okay, do that. And then let it go. It's going to keep going forever because we turned the friction off, right? Okay. So what I want to do is that's going really fast. You can click the slow motion. Okay. And so I want to put this line right on the lowest point. Oh, did I get it or not? I gotta wait. Try to get that red line right on where that little point is. That's pretty good. Maybe go down just a little. I'd say that's pretty good. What?
Should we just take your number for the red line?
No, you can play with that at least. You can still go with my numbers if you want, but
That's what I
you
meant.
should be able to click the red line, a movable line, and move it down. Trying to get it so that it's still a little further down, isn't it? Because the arrow should like point right to the line. Ooh, that was money. I clicked on the slow motion thing over here. It's hard to do if you don't do that. That is good. Okay. So I'm going to grab a ruler and bring it over here. And I'm going to measure from that blue line down to here. It looks like 81 to 82.5.
Yeah.
You're just straight up 82. I'm gonna go 82.5. Okay, 82.5. That is our total distance that it's gonna fall. All right. So what else we got in part 4 here? Let's see. Measure the distance from the starting line to the line of lowest descent using the movable line and ruler. Use the top of the mass as the measuring point. We're actually using the little end of the hook. Calculate the amount of total energy available at the beginning. That's part 4. Okay, so that's pretty easy. Part 4, how much energy does it have when we're holding it up there, ready to pull it, ready to drop it? What kind of energy is it? It's only gravitational because it's not pulling on the spring right yet. Does that make sense? Okay, because we took it so that the spring was uncompressed. It was just sitting there. We held the mass right on it. And at the top, it's all gravitational potential energy. And the equation for that is M times G times H, right? That's the total amount of energy at the top. Okay. Which, by the way, means when I let it go and we don't have any friction, we're not going to lose any energy. That will be the amount of energy that's in the system at all times, even at the bottom, even halfway down. This will be the total amount of energy that's always available. Now, it won't always be gravitational potential, right? It'll be the other forms that various times. Okay, but this is the maximum amount of energy. So I'm going to just come here and I'm going to do total energy equals, and then right here in this next cell, I'm just going to do equals, what was the mass? 0.250, right? 250 grams, 0.250 times 9.81 times, how far did it fall? 0.825, I think mine was. Okay, it's MGH. So 0.25 times 9.81 times, I did 82.5 centimeters, so 0.825. Okay, so we get a little over 2 joules of energy that's in this system. Okay, in part 5, I'm going to just real quickly, I'm going to record my height. My height was 0.825 meters. Okay, I'm going to record that real quick because we're going to use that, reference that. Okay, part 5. Knowing that the GPE at the beginning should equal the EPE at the bottom. Does everybody agree with that? So at the top, it's all gravitational potential energy. As soon as it starts falling, what do you got? You got some kinetic that's moving, right? But you also are starting to pull the spring. So now you also have some elastic. It's going to go down. And if I added all those up, if I added the elastic, I added the kinetic, and I still add how far up it is, the gravitational, it would all equal about 2 joules. At all times, it's going to equal like 2 joules all the way down, right? It goes down, it speeds up, and then it starts to slow down again, and it gets all the way to the bottom, and now it's the bottom, so there's no gravitational potential energy left, right? Okay. There's no kinetic energy either because it's 0. It's not moving, right? So it's all what? It's all elastic at the bottom, right? So what we can do with that, what we're supposed to do here in part 5, is to calculate the K value. Okay, so if we just look here at the board real quick, at the top we have MGH, and at the bottom we have 1/2 K D squared, right? Okay, we've already calculated this part, right? So this was potential energy. We have that number. So that number is 1/2 KD squared. So the K value should be 2 times the GPE, right? Divided by the displacement that we've stretched it all the way out, right? Squared. Okay. So let's use that to figure out our K value right here. Let's do K, and then I'll just do underneath it. I'll do, well, let's do it this way. Let's move that over to the right side. K equals, and then here, I'm going to do left side on that. And this would be equals, and I do a 2, right? 2 times this one right here, gravitational potential energy, or total energy. Okay, and I can do dollar signs there. Oh, we're not going to drag it anywhere. Yeah, we're not doing anything with it, so I guess we don't have to. So 2 times that, and then I'm going to divide by, ooh, I put my height right here, so I can grab that one. That's my D. Now I need to square it. How do you square it? Caret to square it. Caret 2, right? Oh. Must be the same spring. That's the same thing we got for the last spring, right? It's close. We figured it out a different way, so it's a little off, different, but that's fine. It's good. All right, part 6. Part 6, knowing that the total energy should equal the GPE plus the EPE plus the KE at any point on the fall. Right, at any point in the fall, if we add up these 3 things, we should get like the 2 joules. Right? Okay. So knowing that, make a data table of, it's a big data table we're going to make. The first column is going to be displacement, how far we stretched it. Second column is going to be the height, how far it is from the bottom point. The gravitational potential energy column. I want an elastic potential energy column. I want a kinetic energy column, and I want a velocity column. Okay? And we're going to fill this table out. Let's just do that first. Let's not get ahead of ourselves. So here we go. Part 6. I'm going to have a height. That was the first one, right? Because everybody was mad at me that I didn't capitalize it earlier. No, I want a displacement first anyway. Displacement, height, GPE, EPE, KE, velocity. Okay, and we're gonna make a chart. And we're gonna analyze it as it's falling. Okay, how often are we gonna analyze it? We're gonna analyze it by taking whatever the height is, like 0.825. We're gonna divide that by 10. We're just gonna divide it by 10, so we have, we're gonna divide it so in intervals of 10 pieces, right? So in fact, what I could do here is I could just do interval. Interval equals, so I'm going to do equals, take my height, divide by 10. Okay, so there's my interval that I'm going to increase it by every time. It'll be good to have that there. So we're going to analyze all the energies after it's fallen 0.0825, and then after it's falling double that, and then triple that, and so on. All right, so here we go. Just let's do the displacement column first. So at the beginning, at the top of the thing, how far has the string been stretched? 0, yeah. So I'm gonna put a 0 in for that, right? Okay, and then the next interval is gonna be the displacement after it's fallen, whatever the interval is. And then we're gonna add the interval on again, and then we're gonna add the interval on again, right? So what's the fast way to do that? There's a faster way. I could do equals, right? I could grab this previous cell, right? And then add plus, right? The interval. That makes sense? Now I'm gonna have to $sign that interval, right? Because I'm gonna drag this down. So what that'll do is that'll always just take the next cell and add it on, and take the next cell and add it on, and so on. Okay, so I'm going to grab that down, and I'm going to drag this down. And how far do I need to drag it? Probably 10 spots. Not far enough. There it is. How do I know that's far enough? Because that got me up to my height, right? Like about 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and be 11. Well, you drag it 10 because you're dragging the equation 10. What was that? This? I did equals this previous cell, the 0 cell, and I plus the interval. Hmm? You didn't get the same numbers? Did you $sign it?
Oh, wait, now they're the same.
Oh, just magically just changed. I saw it. It just went poof, and it was amazing. Okay.
The last number is the same, I don't think.
Everybody have our displacement column, right? Okay, we're going to do our height column. So at the top, how far up above our bottom line were we? Yeah, we were equals this, right? I could just do equals that. Correct? Okay, and then we started falling. So what do I do here? Equals, I take this cell and I minus this interval, right? Put dollar signs in there. And I should be able to drag that down the same distance and it should end at 0, right? So here's the height, we're falling. Here's the displacement, we're stretching the spring.
It's just
Completely symmetrical, of course, yes. Okay, GPE, how do I calculate it? So that equals, what's the mass? 0.250, right? Times gravity, 9.81. We're going to hard code those in. Times, now what? The height. Where's the height? It's over here in the height column. So we're at the beginning. We're going to have that. And you'll see that that's going to give us our max amount of energy, which we already did. We calculated this already. Okay. Everybody got that? Can I hit enter?
What did you put in this
So we got people behind now, huh?
equals this?
You're back to the height. Okay. So the height I put in equals this height
Yeah, I did
for
that.
my first one. Then the second cell, for the second cell,
Yeah,
I did equals that previous cell
yeah, minus.
minus the interval.
Mine's not right though. Okay, can I drag it?
She's separating I think she's skipping every other cell. So I think she didn't go to the cell right below the first one.
Oh, is it because I dragged this?
You're not supposed to drag the first one. You're supposed to drag your equation one.
These two columns don't need to.
Oh, okay. Oh my gosh, that's why yours was the same, but it wasn't 10 columns, it was 8.
No, it's 10 columns.
I don't know that.
It's not columns, it's rows. It's 10.
Yeah, check it. 1, 2, 3.
Okay, you got it fixed?
I think so.
Get everybody else fixed? Okay, so GPE, did everybody get that equation? This one? It's mass, gravity, height. So 0.25 times 9.81 times, and you gotta hit this height cell. What? That's it for that. And we're gonna drag that down and see how the gravitational potential energy changes. And of course, it gets smaller and smaller until it's the bottom and doesn't have any more left, right? Okay. All right, how do we get the EPE? Equals, right? 0.5. Type in a 0.5. So far, so good?
No.
Where are you at, Grant? Where are you at? They got him. They got him. They got him covered. I'll go if you keep him going. I'm putting it on you. Equals 0.5 times, what do I need next? The K value, and there it is right there, up in part 5. So I'm going to click it. Do we dollar sign it, you mean? Yes, because we're going to drag this down and I don't want that changing. Okay, 1/2 K times, no, not necessarily. But whenever I'm going to one cell and one cell only at all times, I just dollar sign both the row and the column. Yep. Never know when you're going to drag over and all of a sudden you're going to need it, right? Okay, times, what is this? D squared. So I'm going to click this cell over here, right? The displacement. Don't need to dollar sign that because I'm going to increment it down, right? I'm going to square it, caret to square it. And return. And now I'm going to drag that down. You'll see the elastic potential energy 0 at the beginning. Does that make sense?
Yes.
It's not stretching it at all, right? But now we're gonna start, watch this, stretch the spring, stretching it out, stretching it further. And we get about 2 joules of energy at the bottom.
Wow.
You got it right, first one.
Nice, good job, Grant. Okay, how are we gonna find the kinetic energy? Oh, what'd you say? Okay. 0.5, we get someone over there, we'll leave someone over here. 0.5 times the K value, but you got a dollar sign, the letter and then number. Okay? Got it? Time, you got the whole thing? Okay, times your first displacement cell. Don't dollar sign that one. Caret and a 2. Got it? Okay, now you drag it down. Drag it down. Okay, how are we going to get the kinetic energy? How are we going to get the kinetic energy?
Energy.
Right, so that's how it normally calculated on the lab, right? 1/2 mv squared. But we don't know the velocities or that stuff, right? So what we're going to do is we know the total amount of energy that we have, right? It's right here, or it's right here, or we actually calculate it right here, right? So I'm just going to take this and I'm going to subtract out this and this, right? Kinetic energy is going to be whatever's left over, right? So here we go. Equals. Ready? Does everybody have an equal sign entered? Awesome. Now I'm good. Now I'm going to come up here and I'm going to click the total energy in part 4. Dollar sign that thing. Yes. Dollar sign that thing. Minus this, right? Minus the gravitational potential energy. And then minus again, and the elastic potential energy. Everybody understand that equation? Okay, you hit return. And we have 0 kinetic energy at the top. Does that make sense? Yes. We drag it down, and what happens to our kinetic energies? Starts to go up, and then it goes back down. It's 0 at the bottom. That makes sense?
Why would it be, oh wait, hold on. Never mind, we're good. But
Okay, let's come down and figure out where our kinetic energy is at a maximum. Right there in the middle, isn't it? Let's highlight that, yellow. Max KE. Click on the cell and fill it with a color. How do I find the velocity now? Now we're going to your equation. How do we find the velocity? What's the equation for kinetic energy? 1/2 mv squared. We want to solve for the velocity, right? So we're going to take 2 times whatever the kinetic energy was, right? And we're going to divide by the mass. And then we're going to square root that. And that'll be our velocity. Oh boy. Oh boy, this is going to be crazy. Here we go. Let's see how long it takes us to write this equation. Equals. Everybody got an equals? Okay. We want to square root this whole thing. 2 options. Squirt, right? SQRT, or the whole thing could be caret 0.5, right? To the 0.5 power is the same thing as square rooting. Yes. For what? Did you go all the way down? Did you drag it all the way down? Or? This one? She might not have dollar signed the initial total energy. What? Did she subtract them? All right. Okay, so here we go. We're gonna do the squirt, SQRT. I know everybody's going to squirt. I didn't know what squirt was. It's like the greatest quote from the whole year. SQRT, right? And then we're gonna do 2 times. That didn't actually spell squirt, by the way. If anybody just spelled squirt, you got to change that. Okay. 2 times the kinetic energy. That would be this cell right here, right? And we don't want to dollar sign that. Divide by the mass, which was 0.250, right? 0.250. And the velocity at the top is 0. Go all the way down, the velocity at the bottom is 0. And right here in the middle, we have a maximum velocity, max velocity. It looks like the mass gets up to about 2 meters per second. Then it slows down to 0 again. A little above it. Okay, here we go. So, part 7. Part 7, where is the KE at a maximum and what is the velocity at this point? All right, we're done with that. 8, click on the show energy graph. Examine the graph
Part 8 just.
with and without friction. What is the difference?
Part 7 is the max velocity.
Here was part 7. Everybody calm down.
Can I just not?
Just calm down. Just calm down. Shake it off. Shake it off. All right, part 8. Part 8, you need to write a 500-word essay. No, that was yesterday. Yesterday I said a 1,000-word essay because it was April Fool's Day and I was tricking them. But today it's reality. 500-word essay on explaining the conservation of energy here with this graph right here. So look at this graph. Look at this graph, what's happening. We have 3 different kinds of energies. Kinetic energy, and it's 0 at the top, and now it's going, that was hard to watch. Let's do this. Watch this. Oh, it already is on slow. That's too bad. Wish I could make it go slower. Okay, so kinetic energy 0 at the bottom, and kinetic energy 0 at the top, right? So it goes up and that's halfway down right there at the maximum, right? Everybody see that? Okay,
Oh, it
Now-
shows you where the
now,
transferring to.
this one is interesting. Look at this. It actually goes too far down, right? This one should be like maximum potential energy right there, which it is. And then it should come down, and according to our graph, should be 0 right there, right? How come it's not? No, I can't change that. They put a height of 0 level. Your potential energy is based on where your reference level is, right? I wanted to change my reference level to here, but they have it hard coded in to not change. I can't lift that up. I wanted to lift that up to where it's supposed to be, but they wanted to make their graph and they had to make it based off a certain spot. So technically it gets down to here, and that's, you know, about where we're at, but it's gonna then go, whoa, whoa. Then it's gonna go too far down, so that's a little off. Okay? Now the elastic energy, look at it. It goes all the way up at a maximum when it's all the way down. And then it's all the way down to 0 when it's all the way up top. Now at any given point, there's all kinds of different, like right there, there's 3 different types of energy, right? If you add all 3 of those bars up at any point, like right there, that bar, and that bar, you add them all up, you get this bar, right? See, this one's not changing at all. That's the total amount of energy in the system. Make sense? Are you getting 500 words out of this? Because I've used at least 500 words.
Oh,
Okay, so there's, you know, so right in the middle there, there's all the kinetic, there's all the elastic, there's the, it goes away. Okay, but all 3 of those bars are all right there in that total amount the whole time. Now, what happens if, and I didn't get this done the other day, what happens if I start turning on some damping, some friction? What's going to happen? Look what happened. There's a new energy that got popped in here. Thermal energy, which is what? Heat, right? That's why it's red. And what's happening? It's just growing, right? It's just growing. More and more friction. And what's happening to all these other energies? This isn't quite going as high anymore, right? Okay. And so this is just starting to fill up our energy. Damping is like making that, like there's air resistance and friction and a spring. We just turned on reality is what we did. Okay. And so this thing, that thing over there, if I let it go, it's not going to go forever, right? It slows down over time. It loses energy to the surroundings, right? It heats up the air around it and that heat travels off. And eventually we've lost all of our energy and the thing's not going to move anymore. Okay. So everything we did on that up to that point was based off of pretending
It goes until it's equal to,
that it was ideal.
it goes until it's equal to.
There is going to be some elastic potential energy because it stretched the spring out, right? Okay. Not going to be any kinetic. All the kinetic will be gone, right? There's still some gravitational because it's based off of, you know, this line, but there would be for us too because it'd be based off this one, right? Okay. So it has some potential to be able to fall farther, right? It clearly has some elastic potential in there, but the kinetic's going to go all the way to 0. All right.